This is a microcontroller. It powers every Arduino that's ever been made, and today I'll show you how you can make your own development board around it for just $1. I'll share which chips I recommend for different applications, plus some lessons I learned that will save you a ton of time and mistakes. Awesome, so you're set on building your own development board. There are endless microcontrollers to choose from, but here are the few I personally use and recommend. First is the STM8. It's ultra low power, very cheap, and doesn't need any external peripherals to run. It has enough of a punch for almost all basic tasks. It doesn't have too much processing, but it really does get the job done. Next is the STM32. It's a big step up in performance from the STM8, with higher clock speeds and more features. The power consumption is a bit higher, and it does require more onboard components to run properly. For example, it requires a 3.3 volt regulator, multiple decoupling capacitors, and sometimes an external crystal. But the STM32 family is extremely versatile, with chips for almost any application. Finally, here's the RP2040 from Raspberry Pi. It's the most capable chip in the list, and while it's a bit pricey, around $1, it has built-in USB 1.1 support, which makes it perfect if you need a direct USB connection. When it comes to programming, the RP2040 is the simplest, since you can program it directly over USB using the Arduino IDE. The STM32 comes next, because it's straightforward to program using the serial connection or ST-Link with STM32Cube IDE. The STM8 is the trickiest to program because of outdated software, but its features may still be useful for some projects. Now, since we're making our own development boards, this will count as bare metal programming, because there's no bootloader on the board. If you go with the ST chips, you'll need an external programmer, such as the ST-Link V2, which is cheap and widely available. I got mine off Amazon, but most retailers will have them in stock. Once you've picked your microcontroller family, you'll need to select a specific model. I usually get mine on lcsc.com because they have great prices and huge selection, so I've left a link to their MCU section in the description. For this tutorial, I'll be using two chips, the STM8S005K6T6C and the STM32F030C6T6TR. The schematics for both boards are linked down below on my GitHub if you want to follow along. I'll be designing these boards using KiCad, which is the software I use most often, but this won't be a full KiCad tutorial. That could be its own video. But I'll highlight the important things to keep in mind when designing a microcontroller board. The first step in designing a board is selecting your power source. I'll be using a USB-C connector for 5-volt input, but you could also power your board from 12 volts or 24 volts using a barrel jack, terminal block, or by soldering the wires directly onto the board. A quick note, if you're powering the board from the USB-C, you gotta pull down the CC1 and CC2 pins with a 5.1 kilo ohm resistor to ground, because this will tell the USB host to provide 5-volt power. Next is the voltage regulation. You gotta check your microcontroller datasheet for the required supply voltage, because most modern microcontrollers use 3.3 volts, older 8-bit chips also often use 5 volts, like the STM8, and some ultra-low power chips run at 1.8 volts. And you'll likely need a dropout regulator. For example, this one's from Texas Instruments, and it lowers 5 volts down to 3.3 volts for the STM32 I'm using. Because in this tutorial I'm making a board with an STM8 and STM32, the STM8 board doesn't need any voltage regulation because it can take 2.4 volts to 5.5 volts directly, and my USB supply supplies exactly 5 volts. But my STM32 does need a step-down regulator because it can only run at 3.3 volts. I'll also follow the datasheet's hookup diagram and place the regulator's input and output capacitors close to its pins. Okay, now we're going to move on to the reset, boot, and oscillators. The reset pin is usually pulled up to the supply voltage with a 10 kilo ohm resistor, and a push button can short it to ground to reset the chip. I also added a small capacitor to ground here to filter noise, but you have to check your datasheet. Also, for most microcontrollers, there will be a boot pin. Make sure to pull that down to ground with a 10 kilo ohm resistor so that it boosts from the flash. You also have to check your microcontroller's datasheet in case it needs an external crystal oscillator. Many STM32 chips work fine with an internal oscillator, but if you need precise timing or USB, you may need an external 8 MHz crystal, and 2 load capacitors to make the whole oscillation work. On this one I have a 12 MHz crystal, but a 32.768 kHz crystal is also common if you want RTC functionality. Now we're going to talk about decoupling capacitors and grounding. Every microcontroller pin that connects to VCC should have a decoupling capacitor. When placing decoupling capacitors, place them as close as possible to the pin. The STM32 boards in particular may require a dozen or more, and this helps filter out noise and keep the microcontroller stable. Also, when designing your PCB, try to use a solid ground plane. This reduces noise and makes routing easier. Next, we're going to set up our headers. Look at the pinout diagram on your microcontroller and lay out the headers logically so that the routing won't cross over unnecessarily. And also for the ST line of series, you'll need programming headers. For example, on the STM8, you'll need reset, swim, 5 volts and ground. And for the STM32, you'll need SW clock, SWDIO, reset, ground, and 5 volts. If you plan to use a breadboard with your microcontroller, make sure to use 2.54mm male headers spaced properly so that the board can be plugged into either a breadboard or using DuPont connections. Now that everything's laid out, we're going to talk about some of the features you want to add. So if you plan on using I2C, make sure to add pull-up resistors. For example, I use 4.7K on the SDA and SCL lines. Also, I added a power LED so that I can see when the board is on. And I used a 1.5 kilo ohm resistor in series with the LED so that it doesn't burn out. I also added an LED that turns on from one of the pins. For example, I used PA15 with a 220 ohm resistor. And this is so that I can debug the microcontroller or just blink it on and off. Also, double check your current rating so you don't overdrive the LED. I have mine set at roughly 10 milliamps, so that should be enough to light them fully and bright. Once your schematic's done, assign footprints. Double check the resistor and capacitor packages to avoid mismatches that make soldering difficult. I like to export a bill of materials and add the parts to my cart and confirm sizes, because you don't want to order the wrong size of components and then you won't be able to add them to the board. Okay, now let's move on to the PCB layout. Make sure to keep the decoupling caps near the microcontroller pins, keep the traces as short as possible, and try to run power and ground wide. When finished, add silkscreen labels, check everything twice, and export the Gerbers. I usually order from JLC PCB because it's linked with LCSC, but really any fab house works. When the boards arrive, it's time to solder. For microcontrollers, I really recommend having a reflow oven or a hot plate, but if you don't have those and you just have a hand soldering station, I recommend tacking one pad first and then aligning the component and soldering on the other pads. For the microcontroller, I like to pre-tin the pads with a little bit of solder, place the chip with tweezers, and touch each pin with the iron to reflow the solder underneath. This helps avoid bridges so that there isn't that much solder on each of the pins. Once everything's soldered, inspect carefully for shorts and you're done. And that's it! You've made your own custom microcontroller development board. Programming it will now be as simple as any other board using the same chip. Let me know in the comments if that was helpful and what other tutorials you want to see. Thanks so much for watching, and I'll catch you later. Bye guys.